Okay, in this video, we'll talk about atomic and ionic radii, and we'll use Coulomb's law and Coulombic interactions to try to justify what's going on with both atoms and ions and their size. First, let's look at the atomic radii as we go down the periodic table. You can clearly see from this diagram that as the number of energy levels increases, then the atom will be larger. It's really important that we say the occupied energy levels because, in fact, every atom has all the energy levels. It's just that most of the time there aren't electrons in them. And so down the periodic table, size gets larger. I think this image will help with that. That happens for all columns in the periodic table, not just 1 and 4a. Next, let's look at atomic radii as we go across the periodic table. You might think that the number of electrons are increasing, so you might think, ooh, the atoms should get bigger. You can clearly see they do not. Sometimes students might think that the size of the atoms across the chart would stay the same because the same energy level. And that's important that we're in the same energy level. But what really matters is the number of protons is increasing all the way across the periodic table, as I'm showing with lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. You can see there's a steady one by one increase. And so that increased number of protons attracts the electrons that are in that same, in this case, second energy level, and the atoms will become smaller. You could also say effective nuclear charge. There's another video on just what effective nuclear charge is, but that, same as the total charge, increases progressively across the chart. As the increasing nuclear charge occurs, that will indeed cause greater force, which draws the size of the electron cloud in closer. So here's a question. AP often will hide a question in another question, in that at first this question might look like this is a bonding question. This may initially appear to be a bonding question because you're asked, which would you expect to have the shortest bonds? But in fact, this is a periodicity question. Pause if you need a moment to consider this question, and then we'll go right to the answer. So based on what you just learned, that in the fluorine group, fluorine is the smallest atom because it has the fewest number of occupied energy levels. And so the fluorine molecule is going to be able to get closer together with smaller atoms than the chlorine molecule with larger atoms. The bond would be longer. And with the bromine molecule, the bond would be longer still. And so whether we're discussing atoms or diatomic molecules, the trend holds. Now let's consider the radius of ions compared to atoms. So let's concern ourselves with aluminum here on the periodic table and think about the aluminum atom versus the aluminum ion. Go ahead and pause and consider that, and then we'll move on. So hopefully you made a choice of the aluminum atom as being larger than the aluminum ion. Let's look at why. The third valence energy level has been removed. It's important to note that these two particles have the same number of protons, But once that third valence energy level has been removed, this will make the aluminum ion, valence electrons, be in an energy level closer to the nucleus. I'll make a sketch. In green, the aluminum ion and the aluminum atom in purple. Atom, larger, in purple, and when those valence electrons are removed, aluminum ion will be much smaller. It's well worth noting that all positive ions are always smaller than their parent atom. Next, let's consider anions. The chlorine or chloride ion and the chlorine atom. Here you'll find that in the periodic table. Pause, consider, make a decision, and we'll look at the answer. So hopefully you chose the chloride ion or anion. Again, well worth noting that these two particles have the same number of protons, but the added electron increases the electron-electron repulsion, which will force the valence electrons a little bit further away, increasing the size of the ion. Certainly worth noting that all negative ions are larger than their parent atom. Now let's take a look at a series of particles that include a cation, sodium, and a neutral atom, and an anion, oxygen 2-. First thing we should take a look at is the number of electrons. You can see that sodium has 11 electrons, but to turn into a sodium ion, 1 electron must be lost or stolen, resulting in 10 electrons. Neon, of course, on the periodic table has 10 electrons, and oxygen with 8 must gain 2 electrons to become oxygen 2-, resulting in 10 electrons. We might think that these then would be the same size. They are not. And so how is that happening? Instead, we must be sure, and well, let's first say that we have a name for this. These ions and atoms that all have the same number of electrons are called isoelectronic. Same number of electrons. Now what we need to take a look at is the number of protons. You can see again from the periodic table that sodium ion has 11 protons, neon has 10 protons, and the oxygen has only 8 protons. Thus, the greater number of protons causes greater nuclear attraction, causing sodium to be smallest and oxygen 2- to be larger. Let's take a look at this last slide and notice that cations in pink follow the exact same trend in the sense that cations down the periodic table get larger, cations across the periodic table get smaller. Same is true for anions. Anions get larger down the periodic table, and anions get smaller across the periodic table. But what we'd also like to look at is compare the size of an atom compared to its ion. We might call it a parent atom and the resulting ion. Again, cations are atoms that have lost electrons, and those electrons will be one energy level closer. Once these valence electrons are gone, the cation will be smaller. You cannot use this as your reason. It's well worth remembering that, but you can't say, oh, sodium is bigger, sodium ion is smaller than its parent atom, because that's always the case. We need to be sure that we say the sodium ion has lost electrons, one electron in fact, or the magnesium ion loses two, and since the valence electrons have been removed, one energy level closer. Opposite with the anions. Anions are in blue, as you saw, and an atom is gained, which increases the repulsion. We have not changed the number of protons. If it's an oxygen anion, there's still 8 protons, but now 2 electrons have been gained, and that 2 extra electrons would cause increased repulsion. Again, well worth remembering that anions are always larger than their parent atom, but that can't ever be used as the reason. We need to be sure and come in and talk about the increasing repulsion due to the added electrons.